Dear Chairman, dear committee, I am David Grasev and I am a PhD student from University of Defense in Brno, Czech Republic, and today I will present you results of our research devoted to battery impedance model identification via a hybrid optimization algorithm. Here is a short outline of our presentation. We will start with the modeling strategy, then we will explain estimation of initial parameters, the identification procedure, and we will present the results. Regarding the strategy of model identification for batteries, we first measure the battery using an impedance analyzer. We obtain this Nyquist characteristics from which we can estimate the initial set of parameters for our model. The model is represented by an impedance circuit, its equivalent impedance circle that models high frequency, low frequency, and intermediate frequency behavior of the battery. So we need to first choose the model, then determine an initial set of parameters for the model, and then select a proper optimization algorithm that fine-tunes the initial estimation and finds the optimal set of parameters. Regarding the strategies, there are two basic paths we can take. The first path, concise, accurate but very demanding initial estimation of the parameters, but thanks to the estimate being very accurate, we can employ a simple and very fast gradient-based or gradient-free optimization algorithm. An example here is a Nelder Mead simplex algorithm, which is a gradient-free algorithm that enables solving basically non-convex and non-smooth problems. But there is a problem if the accuracy of the estimation is just slightly off. We risk ending up in a local minimum. That's the reason why we choose the second path, where we perform very rough but very quick and smooth estimation of parameters from the Nyquist plot, and then we employ a rather sophisticated hybrid algorithm that will seek the global minimum. And it's also more user-friendly. Regarding the estimation, there are three main processes in the battery that has to be modeled. The low-frequency diffusion, high-frequency induction, and medium-frequency interfacial processes. A common simplifying assumption for the initial estimation is that the processes are independent. They do not affect each other. Here you can see the equivalent impedance model, which consists of 11 parameters. And we start with the low-frequency diffusion process modeled by a constant phase element of Warburg type with the fractional order alpha W parameter and the Warburg capacitance W parameter, or Warburg W parameter. These parameters can be estimated from the geometry of Nyquist characteristics in the low frequency region, where we take a slope starting from the point of minimum frequency. It's a slope of a tangent starting from a point of minimum frequency at basically at the low frequency region, as I already mentioned. And then we compute the W parameter using a very simple algebraic equation that is not stated here, but you can find it in proceedings. Regarding the high frequency inductive processes, the approach is very similar. These processes are modeled by inductive CPE with an inductance L and fractional order slope alpha L, which can be again in the same fashion read out of the Nyquist plot in the high frequency region using a tangent to the Nyquist curve. The most challenging, undoubtedly most challenging processes to model are the interfacial processes, which are modeled by basically three elements connected in series, one standard resistance, and two parallel connections of a CPE, of capacitance CPE, and resistance. The identification of the resistance is very simple. It's the point of intersection of the high frequency inductive process slope, tangent, with the real axis. Regarding the medium part of the Nyquist curve, that is replaced by a symmetrical curve that consists of two semicircle parts. We identify the boundary frequencies Fy and Fx as intersections of both slopes. As basically the intersections as can be seen in the figure, and the point of basically minimum imaginary part of impedance between the medium frequency and low frequency processes. And then we basically compute these frequencies based on an assumption that the ratios between the successive frequencies are constant. So the ratio of Fy is equal, Fy to F1 is equal to the ratio of F1 to Fz, etc. What I forgot to mention is that this is based on a conversion of parameter sets C alpha to parameter sets F alpha, where F is the characteristic frequency of the given CPE. And the reason for this is that it is simpler to obtain these frequencies from the Nyquist curve. There are simple relations that basically enables us to compute F1 and F2 using only Fx and Fy. This relation is not mentioned here, but it is again in the proceedings. And also there is a strong physical interpretation for these frequencies. Regarding the identification or the optimization algorithm, we basically used a hybrid optimization algorithm that consists of a particle swarm optimization for a global search and identification of global optimum candidates, and a Nelder-Mead algorithm that performs a local refinement of these candidates. There are two main loops. So we start with the PSO and Nelder-Mead. If the iteration of the entire algorithm is a first iteration, we basically first need to initialize the overall global error of identification. So we run the PSO, then we perform first fine-tuning using Nelder-Mead. If there is a significant improvement or reduction of the error using the first utilization of Nelder-Mead algorithm, then we run multiple times the Nelder-Mead algorithm in an inner identification loop, which performs further refinement. If basically the improvement is not significant, then we basically continue. If the iteration is larger than first iteration, then we basically, if the improvement is good enough, we can skip the inner Nelder-Mead loop, and if the iteration is larger than 1, we can continue. So we compare this new local best error with the global best error, and if there is no improvement, that means if the difference between the errors is larger than the tolerance, then we basically did not improve the global error and the algorithm is in idle state, so we update the idle count. And if the number of idle iterations, subsequent number iterations, is larger than 5, then we basically end the algorithm, because there is a high probability that we cannot improve the parameter set anymore. Whereas if there is an improvement, we update the global error using the local error, and we reset the counter, and we reinitialize the entire loop, as there is still chance that we will find a better set of parameters. If the tolerance, if the difference between two successive updated global errors is smaller than tolerance, then the algorithm converges. We demonstrate the algorithm on this lithium-ion battery, which was measured using a BioLogic SP300 potentiostat, and for the identification we utilized a computer with these hardware and software specifications. Here you can see the measured Nyquist characteristics, and you can see the frequencies, the minimum and maximum frequencies and the boundary frequencies, as well as the fractional slopes of the fractional order elements. And here you can see the initial estimated parameters using the rough method. Here is the comparison. So here you can see the performance of the initial set of parameters is the green curve. The blue curve here is basically using only the Nelder-Mead algorithm, starting with the same initial set of parameters. And here you can see the results for the hybrid algorithm, which is the green curve. And you can see that the green curve aligns much better with the measured data, which is the red dashed curve, than the local Nelder-Mead optimization. And quantitatively, we can compare the root mean square errors. Here you can see that our hybrid algorithm achieved 3 orders of magnitude less error than the sole utilization of Nelder-Mead algorithm. And you can compare the magnitudes of the identified parameters and notice also the uncertainty in parameter estimation. For some parameters, for example the inductance, you can see that the hybrid algorithm traveled much further and basically found much better estimate. However, the computational time for the hybrid algorithm was almost 20 times larger. So that's the cost of this algorithm. We can arrive at a better parameter set, possibly the global minimum with higher probability is a global minimum of the constrained parameter space. However, the computational time is significantly larger, so it depends on what is preferred. Regarding a future research, it's not that much of a future. We are already working on it, and it's an interactive data processing tool or interactive analysis tool where we will basically combine the model building tool, simulation tool, optimizer to a single interface where the user can or will have an option to select the model, cost function, the algorithm, and possibly also perform fine-tuning of the cost function, for example using a horizontal or vertical segmentation of the frequency domain to tailor the best cost function that suits the given battery. It will be also heavily dependent on users' knowledge or expertise in the field of EIS and battery identification. So that was all from our side. Here are the conclusions. So we developed a hybrid optimization algorithm to identify impedance model for a battery using a rough and very quick estimate with a more accurate, or let's say more demanding but more robust optimization identification tool, optimization/identification tool. And in the future we will answer the open questions during the ongoing development of an interactive analysis tool. And that was all from our side. Thank you for your attention, and we are ready for your questions.